two unique things about Software Mill. So first of all, we've got a fully flat organization structure, so everyone is a CEO. And additionally, we don't have offices. No offices, everyone works at home. And today I would like to help you fail your Cassandra-based project. So during this presentation, I will show you some ideas leading to failure. And they are actually real-life based. So some comes from my personal experience, some from my colleagues, and some other sources. But maybe first, one small question to you. So who actually uses Cassandra? Yeah, nice. And who does not know Cassandra at all? Okay. So a very short introduction. First Cassandra version was released in 2008. And currently we're having Cassandra version 3.10. And there is still a developed branch 3.0. And this is like a stable branch, for example, for DataStax distribution. So as mentioned on previous talk, DataStax is a company who offers a commercial distribution of Cassandra. And Cassandra is a NoSQL database. So this means that we are not having here any ACID, any transactions or full consistency. So, well, it's eventually consistent database. And additionally, it has a bit different data model than we are used to. So it's a columnar data store. We've got tables which are not connected using any relations. And tables can have different column types. So there are some standard primitives. But for example, also we can have collection type columns, where additionally collection elements can have some predefined schema. And there are some limits related to querying for such tables. There are very specific keys for Cassandra tables, but I will talk about that also later. Cassandra has a built-in replication mechanism, so you have to actually define how many copies of your data you want to keep in a cluster. And there is no single point of failure. So every node in the cluster can handle the requests, and every replica can handle both reads and writes. And Cassandra scales great. Largest Cassandra cluster has already over 115,000 of nodes, and stores over 10 petabytes of data, and it's deployed at Apple. And now let's imagine that your boss comes to you and says that, well, you're having a new client who wants to build a startup, and he is very passionate about his idea. And he would like to trade potatoes. And this client says that, well, there are over 4,000 types of potatoes in the world, and only some of them are tradable in every country. For example, in UK you can buy 80 types and US 200 types. But he wants to make them available worldwide. And additionally, he wants to build some additional features. He wants to build some social platform related to potatoes. He wants to measure sizes of sent potatoes, etc. So he has a lot of ideas. And this client is a bit technical. So he claims you're going to have a lot of data, but this will be big data issue. And he have heard about Cassandra, and he says that this will be the right choice for this problem. And he also thinks about that because for Apple it worked, so for potatoes it should also work. So this was the first idea, that having a lot of data indicates that it might be a good idea to use Cassandra. And you react to such client first with some enthusiasm, because new client, new challenges, some interesting technology to use. But then some questions starts appearing. So you are not really sure how much data you're going to have in your problem. You ask your client about requirements, maybe about access patterns, which are very important in case of databases. But client says that he does not know yet. He says that it's a startup and he wants to be agile, so no requirements. And you should be very careful in such situation because you are not sure what will happen next. You are not sure if you will need some transactions in the future, or if you will need, for example, full consistency, which is not possible in Cassandra so easily. And this was also noticed by ThoughtWorks in the technology radar, but you should use Cassandra carefully, because some people start using Cassandra as a general purpose database when really it's optimized for very specific usages. And let's say that you have checked Cassandra, evaluated it for this problem, and well, it should work. And now your boss comes again to you and says that, well, you don't have too much in-house Cassandra experience in your company, so maybe let's start some traditional approach. Let's start from implementing our domain model in Cassandra, and then you will start worrying about the queries, etc. And actually in Cassandra, it's a mistake, because there is a very specific modeling methodology. This methodology was published in form of scientific paper by Artem Chebotko, who works at DataStax. And well, in the first step, you actually need to model your data in form of conceptual data model. So just in form of some entity relationship diagram. So you need to know all the relations between potatoes, between users, that users can have some favorite potatoes types, etc. And apart from that, you need to have whole application workflow. So graph showing all the views in your application, all the queries, and transitions between those views. And then you perform the mapping. You apply some mapping rules, and you combine this entity relationship diagram together with this workflow. And result is the logical data model in form of the Chebotko diagram. And I will show you such a diagram in a moment. And when you have such diagram, you can apply some optimizations and actually produce the physical representation in form of the SQL, so it's Cassandra query language. So, Chebotko diagram. It's just a combination of the queries which needs to be performed together with tables which contains all the data needed to view some data on your website. So, query 1, there is find potatoes by group. So you can imagine that website may have some potato filtering feature, like to filter potatoes by group, because potatoes are separated to main 7 groups. There are red, white, yellow potatoes, etc. And that's why we're having this table. And this table contains field group, which is marked as partition key. And for now, important part for you is that when you have partition key and you query using partition key, then it's an efficient query. And apart from that, there is a name field. And it's marked as clustering key. And for now, it's important that when it's clustering key, it is possible to sort that entries using this name. And about keys, I will also talk more later. And there is some photo, because list of potatoes in a group would just be list of names together with some photos. And user would click entry on such list to go to the potato details. So there is query 2 and new table potato. And there are some other fields, description, possibly some average dimensions, other photos. So everything what is needed to display the new view. And in the other part of your system, they may be some user profiles. And users may have some favorite potato types. So there's another table, potatoes by user, which just allows you to display small list of favorite types. And again, when user clicks entry on such list, this would get him to the potato details. And one thing you may notice here is that we're having here already some duplicates. So photo ID is for sure in potatoes by user and by group. There will be some photos also in the details. So you're having your data duplicated. But it's pretty normal in Cassandra. But unfortunately, if you would like to change such photo, you need to update all the tables. And let's say that you have modeled this part of the domain, And now your client comes in again and says that, well, I would like to add a new view to our application. I would like to query the potatoes by dimensions. And we're already storing dimensions, so it should be easy, right, in Cassandra. And actually, it's not so simple, because you can't query using any field you would like to. And to explain you why, I have to show you how looks the Cassandra cluster. So, nodes in Cassandra cluster creates a ring. And with ring, there is some hashing function, also mentioned on the previous talk. There's a more free function. And this function produces values from minus 2 to power 63 to plus 2 to power 63 minus 1. And all the nodes in the cluster divide those hash values range between them. So every node is responsible for a part. And now, there's a key space. So key space is like a schema instance, the database instance. And key space contains just some tables. And each table contains partitions. And partition is a very important thing here. So partition can be a single row, but this can be also a set of rows. And if you want to have multiple rows inside the partition, then usually you have some clustering key. And partition is just defined by the partition key. And when you want to insert the row, then Cassandra takes the partition key from that row, calculates hash from it, and checks which node is responsible for this part of the range, and puts this row on that node. And when someone would like to query using partition key, then it's also easy, because it would like also just take this partition key, calculate hash, and read from one specific node. So if you have hundreds of nodes in a cluster, it still knows what specific node it needs to query. But what happens when you would like to query using some other field, which is not a key? So there are some options. There are secondary indexes, but they are quite limited. With secondary indexes, you can only perform equality comparisons. So for filtering for dimensions, it won't work because you can't do the range queries. And additionally, it's recommended to use secondary indexes when you have some low cardinality values. And there are some other drawbacks because secondary indexes are kept on every node in a cluster. So when you would like to do some query using secondary index, in the worst case scenario, you would need to check every node, specifically every index on every node to find the value. So it's not efficient. And another option are materialized views, which were added in Cassandra 3.0. And they just allow you to create some views of existing tables by a bit recomposing existing keys for that table. But here you would try to put these dimensions to key, but it's not so simple because keys are often usually filtered using equality comparisons, and you can only filter using range queries for clustering keys and even the last part of the clustering keys, because you may have multiple parts of that key. So it's not so easy, and this may also not work for you. And there's a third option. There are SASI indexes, which are assistable attached secondary indexes, and they were added in version 3.4. And they are much better than original secondary indexes, and they actually allows you to do range queries. So they may work for this case. And there is one more thing related to querying. When sometimes you will perform some query, Cassandra may tell you that, well, you can't do that query without specifying the keywords allow filtering. Because Cassandra by default forbids to do anything what is not efficient. And when you are sure you want to do that, you can add those keywords, and then Cassandra will load some data coming from that query to memory and filter in memory. And depending on the query, it may be very bad or a bit less bad. For example, if you would query a single partition and you would like to filter using some additional field, then depending on the size of this partition, this might be a good idea or not. Because if you would like to load thousands of records to memory and filter them later, this might not be good. So now your client comes in again with another issue. And he says that, well, we had in our user tables field name, and we need to split it to 2 separate columns. And additionally, we would like to change some values. We had potatoes dimensions, and he wants to change units, and do this quite quickly. And in a relational database, this might be quite easy for changing some value and to multiply some specific column values by, for example, 1,000. In a relational query, it's quite simple. But Cassandra does not allow for such operations. SQL is quite limited. And Cassandra won't allow you to do things which interact with a whole cluster, because it likes to save the performance. And concerning this name and the split, in SQL it might be also possible in relational databases to do that using some single magical query. But in Cassandra, you need to add those new columns. You need to manually split that values to put specific cells manually to write the program. And there are some limitations related to the schema changes. So you can add new columns, you can rename some columns, but not all of them. So usually when you would touch some keys of a table, it won't be possible to do that. So often you may encounter the need to create a new table version. So you may have user version 1 table and user version 2 with a different schema. And then you need to manually migrate your data between those tables. And you may write your own application for that, which would load all the data from one table and map this to other format and partially save to another table. But then you have to handle all the parallelism, all the timeouts, retries, etc. So this might be quite hard. And another option is just to use Apache Spark. So you can deploy the Spark cluster near Cassandra cluster. And in Spark, it's quite easy to just define transformation, data from one table, changing some values, and save to another table. And Spark can automatically just parallelize this. And now, let's say that our application goes to the production, and your boss had a great idea, and he has bought cheaply some 2 large machines. And he says that these machines have plenty of memory, very large hard disks, and they should be great for the Cassandra. And it's also not true. And to explain you why, first I have to show you how looks the Cassandra write path. So, when you perform a write in Cassandra, first of all, write is appended to the commit log. And commit log is some structure on a hard disk, which is used when you reply some operations when your node went down, after your node went down. And apart from the commit log, you apply this write to the mem table. And mem table is just some in-memory table. And this mem table, every some time when it reaches some size, is flashed to the disk to form of SS table. And important thing is that SS tables are immutable, so they can't be changed. So in case you will perform some insert, this insert may land in SS table number 1. But when you would do then some update, changing some single cell value, then this update may land in SS table number 2. And when someone would like to read this row, Cassandra need to read 2 SS tables. It knows which tables by some Blum filters and some indexes. And it needs to merge it with current state of mem table and then can return to the client. So this means that over time, number of tables it needs to read grows. And additionally, you're still having old values on the disk. So value was changed by the update, but the original value still exists in first SS table. And because of that, Cassandra has a compaction mechanism. And there are now 4 compaction strategies. One is deprecated. And today I will focus on size-tiered compaction strategy. And it's recommended for write-heavy workloads. So let's say we're having situation like this on the left part of the slide, where we have two small SS tables and one bigger one. And during compaction, Cassandra will choose SS tables which have similar size and will compact them together. So those two small ones will produce that larger one from the right side. But important part is that those tables are immutable. So Cassandra will first read those old ones, write new one, and then when it will be finished, it can delete those old ones. So this also means that in the worst case scenario, you need to have half of your disk free, because if your data takes half of your hard disk and you would need to do some big compaction, then new tables will also take the half of your disk. And when those new tables will be produced, then you can delete the old tables, so again you have half of your disk free. This is drawback specifically of the size-tiered compaction strategy. And during compaction, Cassandra needs to read those tables, so there is used some disk throughput for read, then some CPU for performing the merges of those entries in different tables, and then again disk throughput to write this back to disk. So compaction generally uses resources. And if you have more and more data in your cluster, so then it is needed to perform more and more compactions. And these compactions takes more time. And when they take more time, then constantly you have some CPU usage and some disk usage. And because of that, there are some recommended maximum disk sizes for Cassandra. So data stacks recommendations first define what disk type you should use. So you should rather use SSDs. And if you really can't use SSDs and you have to use spinning hard disks, then use at least two of them. So one for the commit log and one for SS tables, so that Cassandra doesn't have to jump too much around those disks. And avoid any network attached storages or SANs, etc. And additionally, you don't need to have any mirroring writes, etc. because you have already replication in your cluster. And concerning disk size. So for size-tiered compaction strategy and average workloads and SSDs, it is recommended to have max 2 terabyte disk per node. And 2 terabyte disk per node means 1 terabyte of data per node. And if you don't have SSD, but just a hard disk, spinning hard disk, then this goes down to 500 gigabytes around. And this strongly depends on type of your workload in the cluster. And the heap size. So Cassandra is a Java application, so it allocates some heap. And when heap grows, there are longer and longer garbage collection times. So for some older CPUs, so below 8 cores, it is recommended to keep your heap below 8 gigabytes. And if you have more than 8 cores, you may experiment with CMS or G1 garbage collection strategies and use up to even 60 gigabytes heap. And now concerning the VMs. So Boss has bought 2 large machines, and now you are sure you don't want them, because large disks, a lot of memory might not be good for Cassandra. And Boss has a great idea to put their VMs. So he says, let's put 3 VMs per hardware machine. And it's also not a good idea, because VMs, first of all, may share some resources, for example, shared disks, so then disk throughput may be limited. But also with 2 machines, when one machine fails, half of your cluster goes down. And when you want to have replication factor of more than 2, then it's even more problematic. So Cassandra prefers to have more small machines than less large ones. And now your client comes in again and says that, well, Cassandra is already running in the production and everything works great, it's fast, etc. So I don't need you anymore. So it can just run and without any interactions, right? And unfortunately, no, because this can result in the rise of the zombies. So there is possibly a scenario in Cassandra when deleted rows starts reappearing. So it seems that you wanted to delete something, but after a few days it appears again in a cluster. And to explain that, I have to show you how looks the whole write process. So let's say that this box on the right side is our application put in some container. And generally, when you have your application, it have defined some seed nodes, and it connects to these seed nodes to get the cluster topology. And then cluster is aware of the whole cluster topology of all the nodes in a cluster, and it can choose to which it wants connects to later. So it can load balance queries, for example, or choose the nearest one, etc. So let's say that it connects to this node. And this node becomes a query coordinator. So our application wants to perform a write. And our F3 in the right corner means that we want to have replication factor 3. So we want to have 3 copies of our data in a cluster. And CL is a consistency level. And quorum means that we want to have acknowledgements from the majority. So application performs write to coordinator. Coordinator sends writes to 3 nodes, but waits only for 2 acknowledgements, and then returns to the client. So it does not really care if this third node was successful with the write or not. And during the read, it again sends 3 read requests, but only waits for 2 replies. And when have that 2 replies, compares the timestamps, and as mentioned also in previous talk, because every cell value has a timestamp in Cassandra, and it just returns the newer value to the client. But what happens when something fails? So when one node has failed, this write will be still successful, because it needs only to have 2 acknowledgements for the consistency level quorum. But then client wants to read some data, and let's say that this node went back, and it is not yet consistent with the rest of the cluster. So it might have outdated data. And when you perform read using also consistency level quorum, it will get data from 2 nodes, compare them, and return the newer value to the client. So client will get the right data. But now, what happens during the delete? So, as I have said before, SS tables in Cassandra are immutable. So you can't modify them just like that. So delete in Cassandra produces Tombstones. So delete actually produces a write. And let's say that it's our initial state where we have some row put to three nodes. So version 1 means just that this row exists in the cluster. And now client wants to perform a delete of it. And 2 nodes were successful. So version 2 means this row was deleted successfully. There is tombstone for it. And this third node was offline. So it couldn't save delete on it. So it has still version 1. And there are some mechanisms which try to make your data up to date in a cluster to synchronize that values. But first, if this node was offline below max hint window in milliseconds, which is by default 3 hours, then the query coordinator stores hint and handoffs. So these are operations. It will try to reply to that failed node if it goes up again below 3 hours. But let's say that our node was offline for a longer time, so this mechanism couldn't be run. And now there's another mechanism. There is a read repair. So if someone would like to read this deleted row, there is some probability, and there is a configuration key read repair chance. There is some probability that Cassandra will run mechanism which will fetch data from all the replicas, will compare them, and will synchronize the outdated values. But here again, there is possible option in which nobody would like to read our deleted row. So then there is compaction. And compaction after GC grace seconds, which is by default 10 days, can actually delete the tombstones with original data. So after 10 days of the event of creating that tombstones, Cassandra can forget about these rows. So this may produce this situation on the left, where those two nodes does not have any info that such row has even ever existed in a cluster. But this node still have our row. And then could be run the repair process. It can be also run manually. And those nodes will look at that node on the right and will see that, well, we were missing some data, and they will try to synchronize. And they will get again the version 1, so the row exists. So this deleted theoretical row starts appearing again in our cluster. And it's pretty easy to avoid such situation because GC grace seconds is by default 10 days. So it is just enough to run repair more often, to, for example, run it every 7 days. And there are also some recommendations regarding running repairs. For example, if your node was offline, just after bringing it back, run the repair. If node was offline for a few days, just throw away data from it and bootstrap it from scratch. If node performs a lot of updates and deletes, then it might be also a good idea to run repairs there. And also if you don't run too much reads, so read repair can't be run. Also it's a hint for running repairs manually. And actually you can run repairs even daily, because you can run some partial repairs in a cluster, but you have to schedule them manually using some cron in the system. And there are some works to implement automatic repairs in Cassandra, but it's still the future. And let's say that now your boss has a new great idea, but there was some feature in the system which required a queue. And he wants to save some money again, and he don't want to deploy a Kafka cluster or something like that. So he would like to use our Cassandra as a queue. Just use some table, put there some entries, and delete them constantly. And actually, it's a worst case for the Cassandra, because it can lead to a tombstone hell. And in this scenario, when you perform a lot of reads and writes and deletes daily, you may end up in a situation when your table looks empty, but your hard disk is full, because these tombstones can be deleted together with original data only after 10 days by default. So this can be full. And additionally, there's another drawback, because they can be deleted after 10 days, but they don't have to. And there's a scenario in which we have, for example, such 3 SS tables, 2 big ones and 1 small one. And this green dot means that there is event related to the row creation. And this right dot is the creation of a tombstone. And in that scenario, if compaction runs, Cassandra will compact those 2 big tables together, creating 1 large table, and we will still have this tombstone in that small table. And size-tiered compaction strategy can compact only tables which have similar size. So it can't compact this with this. So it will have to wait until this small table grows in size to the size of that 2 together. So this can take days, months, depending on your data. So these tombstones may exist in your database for months. And I have seen also some presentation where they had a scenario in one company where over 60% of their tombstones were still existing in a cluster a few months after creating them. So we have to be careful with that, deletes. And some other smaller ideas. To use load balancer. And as I have mentioned before, cluster, when knows the cluster topology, can automatically just load balance queries among all nodes in a cluster. So bringing some separate load balancer is just another point of failure you don't want to have. And to use Cassandra as a search engine. So when you want to perform many filterings in Cassandra, it may be needed to create many tables, many materialized views. So this may be hard, may need a lot of work, and also not everything is possible. For example, when you want to perform some full text search, you may need some additional plugins. So this might be a good idea to use some external system like Solr or Elastic or something like that. And to use Cassandra as a file store, especially when you have large files, this also might not be a good idea, because these files need to be put on all the replicas, need to take part in read repairs, compactions, etc. And there are really existing other systems dedicated for file storing in a cluster, which would be much better. So some wise men have said that trying is first step towards a failure. So if you want to try to use Cassandra, you don't know if you will succeed. And also, failure is the opportunity to begin again more intelligently. So you learn on your mistakes and you are able to make next project more successful. Small summing up. So carefully check if Cassandra is for sure for you. If you really have a big data problem, if you can't use just a relational database. Check also for the transactions, consistency issues. Do you can really have a lot of duplicates of your data in a cluster? And start from the queries. So verify if all queries are possible to be modeled in Cassandra, because this may be really hard sometimes. And choose hardware very carefully. So don't use too large disks. Prefer more smaller machines than less large ones. Avoid deletes. In perfect scenario, don't have any deletes at all. And even Cassandra prefers scenarios when you even don't have updates. So all the problems with append-only data, event sourcing, etc. are just perfect for Cassandra. And monitor your cluster. Check garbage collection times, check requests times, etc. But also maintain your cluster. So schedule those repairs and check compaction times. Check if data is synchronized, check if these repairs are really running. Some learning materials. There is our company blog where we have also blogged on Cassandra monitoring. Then a link to the ThoughtWorks technology radar together with that point I have mentioned Cassandra carefully. And third link is the link to DataStax Academy. And they have their online courses related to Cassandra. There are now around 5 courses, 3 related to base Cassandra. There is some core concepts, some data modeling, and Cassandra administration. And 2 related to the DataStax Enterprise and these features. And if you would like to learn something about Cassandra and how it works underneath, this might be a very good place to start. Next link from the last pickle blog about deletes and tombstones and how this exactly works underneath. And link to the hardware planning guides from the DataStax. And that's all for today. If someone would like to grab some stickers, just come after the talk. I have more than those 2 types with me. And do you have any questions?
Hi, I have one question because it is related. I was interested about the Cassandra to introduce it in one of my microservices, but I have read in DataStax they told that in fact I should create the new table for each query with the filtering. Yeah. So let's say I have the table with X, Y, Z columns, and I would like to search once by X, once by Y. Then I should create the new table, and
yeah. So below Cassandra 3.0, there were no other options. It was the only possible choice to model query to create a table per query, and it was the best choice for the performance perspective. And from 3.0, we have also that materialized views. So they can help sometimes because when those tables per query, you have many duplications to keep up to date and up-to-date data, etc. So you need a lot of work during the updates of that views. So materialized views, for example, can help in such situations, but they have also some drawbacks related to performance because they need to update all the views. And SAS indexes are also quite new, and they have some advantages and disadvantages. So it depends on your problem, but yeah, creating table per query might be sometimes the best choice.
Okay, so last question related to first one. So it means that, for example, if I need to 3 different queries by 3 different columns, then I need to have 3 different tables, and when I want to insert some element to my system, I need, in fact, update 3 different tables in
exactly.
one. Okay.
And because of that, those materialized views were also created because then Cassandra does that automatically. If there are no more questions, you can grab me later during the break or tomorrow, and thank you.